Hello everyone, welcome to lecture 2.1. In this lecture we're going to introduce cuda C versus thrust and other cuda libraries. The objective of this lecture is for students to learn the main venues and developer resources for GPU computing and thus understand where cuda C fits in the global picture. There are at least three ways to accelerate an application using GPUs. Here we show the picture of an application on top, and these applications can use one of the three venues for accelerating various parts of their computation. On the left-hand side, we show the libraries, and these libraries are written by experts, and they perform some very commonly used computation, and they're very easy to use. And whenever you can use them, you get very high performance. The middle part is the compiler directives. And a good example is OpenACC directives. And these are the directives that a developer can annotate their sequential application so that the compiler will do the parallelization and performance enhancement for the developers. These things are easy to use and they result in portable code. And on the right-hand side, we show the programming languages approach. And these are programming languages that are especially designed to be able to use the GPU effectively. And this tend to have the best performance and most flexibility, but it does require some significant effort from the developers. This course is going to be focusing on the programming language approach. The idea is that once the students can fully understand how to write a piece of computation to be performed on the GPU using programming languages approach, then the students can make very effective use of compiler directives, and the students can also understand how to best use some of these libraries. Whenever the computation to be accelerated can fit into one of the available library function patterns, the library approach provides an easy, high-quality acceleration to applications. These library functions can be used by developers who don't have in-depth knowledge of GPU programming. And if the original application is already using some libraries that has GPU accelerated versions, then the GPU accelerated versions can be dropped in and provide immediate acceleration. The libraries tend to be developed by experts and tend to offer very high quality implementations of the functions that are encountered in a broad range of applications.
NVIDIA provides a collection of GPU-accelerated libraries that target a wide range of computing applications. Again, these libraries provide drop-in GPU acceleration for developers and can be enabled with only minimal changes to existing codes. Each of the NVIDIA accelerated computing libraries falls into one of four categories: deep learning, linear algebra, signal image and video processing, and parallel algorithms. Collectively, the libraries in the deep learning category accelerate all aspects of the deep learning computational pipeline, from model creation to training to inference. These libraries are used to accelerate a number of widely used deep learning frameworks on GPUs, including Caffe, MXNet, TensorFlow, and PyTorch. Some of the deep learning libraries include cuDNN, a library of primitives for deep neural networks that includes highly tuned implementations for forward and backward convolution, pooling, normalization, and activation layers. TensorRT, a neural network inference library for building deep learning applications. And DeepStream SDK, an advanced GPU-accelerated video inference library. In the linear algebra category, there are a number of GPU-accelerated math libraries. These libraries include routines that are widely used in scientific and engineering applications. For example, the cuBLAS library contains basic linear algebra subroutines, BLAS, for dense linear algebra applications. cuSparse contains the similar BLAS subroutines for sparse matrices. And cuSolver includes implementations of direct solvers, both dense and sparse, that are widely used in applications within computational chemistry, CFD, computer vision, and linear optimization. The signal, image, and video libraries include various signal processing functionalities. For example, the cuFFT library provides fast Fourier transform implementations with an API that's similar to FFTW. NPP, or NVIDIA Performance Primitives, is a GPU-accelerated library for image and signal processing. And the NVIDIA Codec SDK includes APIs and tools for hardware acceleration for video encoding and decoding applications. The fourth category, parallel algorithms, provides tools for constructs that show up frequently in parallel computing, such as sort, reduce, scan, and collective communication. The NVGraph library provides high-performance parallel algorithms for graph analytics applications. Nickel, or the NVIDIA Collective Communications Library, provides collective communication primitives, such as all reduce and all gather. It's used for the efficient scaling applications across multiple GPUs and multiple nodes. And finally, the Thrust library provides implementations for parallel algorithms and data structures that are designed for heterogeneous, high-performance computing. Thrust uses an STL-like interface that should be familiar to any C++ programmer. The NVIDIA accelerated computing libraries provide highly optimized kernels that are periodically maintained and updated for new GPU architectures. Developers should familiarize themselves with these libraries and consider using them when developing new GPU code.
This slide shows a simple vector addition example when using the Thrust library. We're going to explain the usage of Thrust library in one of the modules. For the purpose of this section, we just need to see that in order to use Thrust, we need to declare the vectors in the GPU device memory, and we need to copy data from the host to the device. And then we just need to call a thrust function that which is transform, that applies the thrust plus operator on a input 1 vector, input 2 vector, and produce a device output vector. The code is simple, and the user does not need to know the details of the implementation of how the transform applies the plus operator to these input vectors and generate the output vector. The compiler directive approach provides an easy portable acceleration. The compiler directives tend to be very easy to use because the compiler takes care of the details of parallelism management and data movement. The code using compiler directives are very portable because the code is generic, not specific to any type of hardware, and can be deployed into multiple languages. However, the use of compiler directives also leads to some uncertainty because the performance of the code can vary across compiler versions or different compilers. In this slide, we show the OpenACC compiler directives. And the OpenACC compiler directives can be used for C, C++, and Fortran. On this slide, we show the example of OpenACC with C programs. And we see that the code is a loop that is a sequential C code, but we add a pragma, which is a compiler directive, that tells the compiler that the loop is a parallel loop, and it also tells the compiler the input data and output data that needs to be copied between the host and device. The programming language approach provides the most performant and flexible acceleration to applications. In this approach, the programmer has the best control of parallelism and data movement, and it tends to be the most flexible because the computation does not need to fit into a limited set of library patterns or directive types. However, this approach tends to be more verbose. The cost of having more control is that the programmer often needs to express more details in the code. Let's zoom a little bit more into the GPU programming languages. And cuda C is not the only programming language in the space.
For Fortran
we
programmers,
actually have
CUDA
quite a
Fortran
few
provides a set of
categories
extensions to enable low-level CUDA programming.
Programming
CUDA
languages
Fortran includes
in
both
the
a Fortran
GPU
compiler
computing domain.
and a programming toolchain.
For example, on top we have the numerical
C++
analytics
and Fortran
languages such as
may consider
MATLAB,
using
such as
OpenACC.
Mathematica, such as
OpenACC is
LabVIEW.
an
These
open
are
programming
the
standard designed to
popular,
simplify programming for
very
heterogeneous
high-level
computer
programming
systems.
languages that
OpenACC
many
uses a simple source
practitioners
code
use
annotation
to
model. It
to
allows
perform
users to offload kernels to a
mathematical
variety of accelerators,
computation
including
and
NVIDIA
data
GPUs.
manipulation. We also
C++
have Fortran,
programmers can also use
CUDA
the Thrust
Fortran,
library.
and CUDA
Thrust
C,
provides a
CUDA
collection of
C++.
parallel primitives and data structures.
These are the more
They are fully
traditional
interoperable with vanilla
workhorse
CUDA C.
languages that
Thrust is
many
implemented as a
experts
template library of header
use
files
in
with an
to
API that
program their
resembles
system.
the C++
And then
STL.
we have the
Several of the most
scripting
popular
languages,
numerical analytics programming languages
such as
can be used with
Python,
CUDA as well,
and we have
including
PyCUDA,
MATLAB,
Copperhead,
Mathematica,
Numba,
and LabVIEW.
and we have
Different
F#,
flavors of
which is
support
meant
include robust built-in
a
functions
language
that use CUDA behind the scenes,
that
and
is,
direct generation of CUDA code within the numerical
based on
computing framework.
the Fortran language.
In the Python
but with,
space, PyCUDA and
good,
Numba are widely used
runtime
for
support.
GPU programming.
And so we have all
PyCUDA is
these
a collection
different
of
languages
wrappers that
can
expose the
fit
full power of the CUDA
the
driver
level
API.
of expertise.
PyCUDA also
and,
includes
the
several
domain,
Pythonic abstractions that make CUDA programming more convenient
support.
compared to the canonical
CUDA
C-based
C
CUDA runtime.
is a very
Another option is Numba,
foundational
an open source
language
just-in-time
that
compiler for
someone
Python.
can learn.
With Numba,
and then,
developers can compile a
the
subset of
knowledge
Python
can
and
be
NumPy
easily
code directly into CUDA
generalized
kernels.
to understand these
Compared
other
to NVIDIA
languages.
GPU
That's
accelerated
why
libraries,
we're choosing CUDA
these programming
C,
languages provide
for
more
this particular
flexibility and
course.
low-level control to the programmer. CUDA programming is often used along with the NVIDIA GPU accelerated libraries in order to simplify the development and deployment of high-performance GPU applications.
So back to the global picture, CUDA C is a programming language support for using GPUs, and so it's tend to have the best performance and the most flexibility. And we're going to learn quite a few skills. And with some of them are general parallel programming skills. Some of them are more specific to GPU hardware utilization. And once you understand these skills, you can start to write very high performing GPU code. And then it will be also very easy to understand the usage, the effective usage of these other approaches. Module 2.1. Thank you.